Hey, welcome everyone to this next lecture. This is on section 7.5 from Hawks, and it will cover equations, both what we call logarithmic and exponential equations. To start, let's just review our basic definition for logarithms. Log base b of x equals y means the same thing as b to the y is equal to x. The left side's called the logarithmic form, and the right side's called the exponential form. Now, since we are going to do a lot of examples today using the base e, that special number 2.718, we're going to use log space e, which we use the abbreviation ln for. Okay, so ln x equals y means e to the y is equal to x. So to start with, let's say we have ln 2x minus 1 minus ln of x is equal to natural log of 5. Okay. Now we want to solve this for x. All right. So step one will be we've got two places where there's x. Let's use our property of logarithms that we covered last time. Natural log of 2x minus 1 minus natural log of x is when you're subtracting, you divide. Okay? So we get natural log of 2x minus 1 over x is natural log 5. So we must have that 2x minus 1 over x is equal to 5. And now we can finish solving for x using just regular algebra. Let's multiply both sides by x. Okay, that cancels the x on the left, so we get 2x minus 1 is equal to 5x. Let's subtract 2x from both sides. And we're going to get negative 1 is equal to 3x, which is going to mean dividing by 3, x is equal to negative 1/3. All right, now there's one extra wrinkle we have to worry about here. Okay. Previously, I've always said that you can check your answer by putting the x back in the original equation. In this case, we have to do that. Okay, and the main thing we're concerned about is remember that logs are only defined if the thing you're taking the log of is at least is bigger than 0. So if we have a negative 1/3, if we take the natural log of negative 1/3, that will be undefined. You can try that on your calculator. It will tell you that there's an error. Okay, so actually, this x equals negative 1/3 is not going to work in the original equation. So in fact, this equation is going to have no solutions. And Hawks will give you an option for that if it's appropriate. You will have no solutions. Sometimes they'll use the null symbol there. Okay, let's say we have 5 to the 3x minus 2 is equal to 17. Okay, and we want to solve for x. Now, this is an exponential form, so if we want to try to get the x out of the exponent, let's change to logarithmic form. Okay, all right. The thing you're taking to the exponent is the base. Okay, the exponent is 3x minus 2, so here's the logarithmic form. 5 to the 3x minus 2 is equal to 17. Okay, all right. Now, let's finish solving for x, and I'm going to leave the log base 5 of 17 there until the end, and then if you want to, you can calculate that out on a calculator using the change of base formula. Okay, so I'm going to add 2 to both sides. Okay, so I have 3x is log base 5 of 17 plus 2, and then I just have to divide by 3. Okay, so x is equal to log base 5 of 17 plus 2 over 3. And this is what we call the exact form. And if you want to have a decimal approximation, you can plug the log part into your calculator. Okay. Using the change base formula, log base 5 of 17 will be, you can use the base 10 logarithm, log 17 over log 5. Okay. Log 17 is about 1.23. Log 5 is about 0.69897. I'm going for several decimal places there. Should be about 1.76 to 2 decimal places. Okay. And now we're going to do a really simple log equation. Okay. Let's say I've got log base A of 30 is equal to 2. I want to solve this for A, the base. Okay. Well, change to exponential form. A squared would be 30. Same thing as we always do. A, the base to the exponent is equal to the number there. And if a squared is equal to 30, we can just take the square root of both sides. Okay. A will be the square root of 30. And we don't have to worry about the negative square root because bases for logarithms are always positive. Okay. All right. Now let's go. We're going to have some application examples here, and these will be very similar to the ones that you're going to see in Hawks. Okay, so and you've seen some of these previously all the way back in section 7.2. So these will be similar equations. The difference is now we're going to be solving for the variable that's in the exponent. Okay. All right. So in this case, we're going to have a equation for concentration of a drug in the bloodstream, given by this equation. C for concentration. C sub 0 is the initial dosage that you administer. Time is going to be time in hours from when the drug is administered. Okay. Now, let's say we administer 100 milligrams of the drug. How long until 40 milligrams remain? The 100, that is your C sub 0. We want to know if that's how much you start with, how long till you have 40. 40 is the concentration after a certain amount of time. What we're asked for is a how long. They're asking us for the time t. So we would set this up as 40 is equal to 100 e to the minus 0.8 t. And I'll solve this for t. First step, divide by 100. That's going to get us 0.4 is equal to e to the negative 0.8 t. All right. Now remember, when you have e to a power, if you change that to logarithmic form, you would use the natural logarithm. Okay? We're going to have ln, natural log of 0.4, is equal to the exponent. Remember, logarithms are always exponents. Our exponent is this, so our log is going to be equal to that. Okay? The only thing we have left to do to solve for t is divide by the minus 0.8. And so t is going to be, the natural log is 0.4 divided by negative 0.8. And I think if you do this out on your calculator, quick on my calculator, yep, 1.145 or so. Or 1.15 to 2 decimal places. Okay. Now, last example, we're going to go back to COVID and use exponential growth to model the COVID epidemic. Okay, so let's suppose the cases are doubling every 4 days or so. That's a little slower than actual. And let's suppose at this point we have 124,000 cases and we want to know how long until we get to 2 million. Okay, all right. We're going to use a similar equation uh, to the ones we've used before. Okay, A0 will be a starting amount, R will be a growth rate, and T is going to be time. Now, the difference here is they don't tell us what R is, but we can figure that out using the fact that cases are doubling every 4 days. What that'll tell us is, okay, however much we start with after 4 days, so if T is 4, we're going to have twice what we start with. Okay. All right, and now we can solve this for the R, and once we know that, we can put in the information about the 124,000 and the 2 million. Okay. So let's solve for R. First divide by A0. 2 will be equal to e to the r times 4. All right, just like before, let's change to logarithmic form. Natural log of 2 will be 4r. And so r will be the natural log of 2 divided by 4. And that's going to be about, we're going to get about 0.173. All right. Okay, so that means our equation now is a sub 0, whatever we start with, e to the 0.173 times t. That's our r. Okay. All right, now we're starting with 124,000 cases, and we want to know when we get to 2 million. Okay, so we're going to put in the 124 for our starting. We'll leave off the 3 zeros. Okay. 2 million, if we cut off 3 zeros, gives us 2,000. Now let's solve this for t. First divide both sides by 124. 2,000 divided by 124. So 16.13 is e to the 0.173t. All right, now we change to logarithmic form. All right, the natural log of 16.13 is equal to the 0.173t. Okay, the base e is gone, but it's like e to the 0.173t is the 16.13. All right, so then all we have to do is divide by the 0.173. And so we'll take the natural log of the 16.13. That's about 2.78 divided by 0.173. That's what our t is. So divide by the 0.173. T is approximately 16.07. If you want to, since we're talking days, that's about 16 days. All right. So under these assumptions, in a little over 2 weeks, we'll go from 124,000 cases to about 2 million. All right. That shows you the power of exponential growth. All right. So this will be the last lecture that we have on Chapter 7. And look on Canvas for information about the test that'll be coming up on Friday. All right.